Okay, so we know that if you're gonna do an integral from a to b, it just means like the area under a curve. But if you look in a math textbook, you'll oftentimes see integrals like this. And there's no a and b. Like, there's nothing in the limits, you know? So you should know what this means. If you don't see limits, so if there's no a and b, if no limits are given, what you're supposed to do on this is just provide the antiderivative part. And then you just stop. Okay? Just find the antiderivative. Okay? So for example, the answer to this question would just be negative cosine x. Why? Because negative cosine x is the function whose derivative is sine x. Okay, now there could be a constant here, right? Like I could put a plus 1 million here, and nobody can stop me, because technically negative cos x plus 1 million is still going to have a derivative sine x. Isn't that true? In fact, we don't even know that it's a million. It could be anything. So when you do a problem like this, you're supposed to put a plus c at the end. And it just means any constant. And this is called an indefinite integral. Okay? Indefinite integral. Not to be confused with an improper integral, which we'll talk about later. Okay? Indefinite just means we don't have boundaries. So as far as we can get is all we can do is just find the antiderivative and kind of stop. Okay? All right. So there's the first one. Pretty simple, right? Here's an easy one for you. E to the x. Can you think of a function whose derivative is e to the x? E to the x plus c. Don't forget the plus c. Very common for students to forget the plus c. Okay, how about this one? Stretch your memory here. Does anyone remember that one? This one is one of the arc functions. Inverse. This one is inverse secant. Arc secant. Plus c, don't forget plus c. Pretty important. Okay? The c is more important than you think, actually. If we hadn't skipped 6-1, you would know why it's so important. Okay, what about this one? Anyone remember that one? Arctan. Good. Plus c. Plus c. Don't forget plus c. Right. Okay, so we're seeing that all we're doing is trying to find the antiderivative. Not too hard. Okay, what about this one? X squared minus sine x. Fine, plus c. Let's put in a plus c. What would we do with that? Let's put in a plus k. K being a constant. Okay, k is a number. Okay, so let's think here. Can you think of something that would yield x squared as a derivative? X cubed would reduce to x squared if you took the derivative. The problem is it comes out to 3x squared. So I need a 1/3 here. If I put a 1/3 here, then the derivative is truly x squared. Okay? Minus, actually plus, cosine x, that would have the derivative negative sign. And what would give us a derivative of k? Kx. Don't forget the plus c. Yeah, actually, we don't want to think that the plus c is some unknown number yet. We haven't found c yet. It's any number. A million, a billion, a trillion, pi, 0, e, or 1/3. It doesn't matter what c is. That's the whole point. In some problems, you're asked to find c. Those are called initial conditions. And in physics class, you're always looking for the c because you're dealing with a particular equation of motion. So, but in this class, you just leave it plus c. And we know that c can be anything at all. Okay, any questions on that? All right. So what about this one? You've got to be kind of careful with this one. Some of you recognize it right off the bat. What is it? ln x plus c. Okay, we have to be really careful with this one. Because what is the domain of 1 over x? Any number you want except 0. But what is the domain of ln x? What are you allowed to plug in to ln? Only positive numbers. Okay? So it's really important that on this particular example that you don't write ln x, you write ln absolute value x. Okay? Again, the reason is 1 over x can receive any number except 0. But ln x can only receive positives, so any domain values that come in need to be absolute value for this to make sense. Okay? It looks like a small deal, but it's kind of a big deal. So please memorize that one. I'll put a star by it. Memorize that one.
So the domains for any derivatives and integrals have to be the same?
No, what I'm saying is if you want to find the area between like -3 and -1 for 1 over x, that has meaning. That makes perfect sense. That means you are wishing to find this area. Okay? But when you solve it, you can't write ln x and then go from -3 to -1. That doesn't even make sense. That makes no sense. ln won't even take those numbers. You try to feed those numbers to ln and he'll just spit them right back out. Okay? So we require the absolute value to do this problem, and then you can actually plug those in. Okay? Does that make sense? Okay. All right, so that one's a memorizer. Let's box that. Don't forget it. What if you run into something like this one? Sec squared r dr. What do you do with that? Can you think of a function whose derivative was secant squared? Tangent, yeah. So is it tan x? Tan r. Our integration variable is r, so let's be consistent. Tan r has derivative sec squared r, right? Okay, what about this one? Sec kx tan kx. Can you think of something that has derivative sectan? Secant. Is it as simple as secant kx plus c? Okay, we've got to be a little bit careful. The derivative of sec kx would actually be sec kx tan kx times k. So we need a little 1 over k to protect against the chain rule on something like this. There you go. This really does have derivative sec kx tan kx. Okay, any questions? All right. Okay, it's going to get harder because now I'm going to start throwing up stuff that you can't solve. So how would you do this problem right here? Let's say you had 2x times cosine of x squared dx. How do you solve this thing? First of all, it seems like there's kind of two things going on. You've got a 2x and a cosine x squared. So what are you supposed to do? Just make this like x squared, because the derivative of x squared is 2x, and then the cosine x squared, just do like sine x squared? Like, that didn't, I don't know, am I supposed to just integrate each of these and multiply them? Or? The answer is no. What you're looking at is a derivative, okay? And so part of it might just be the result of the chain rule. Okay? So actually the answer to this problem is simply sine x squared. Okay? The answer to this problem is simply sine x squared. Why? Because what is the derivative of sine x squared? Oh, and plus c. What's the derivative of sine x squared?
Cosine x.
Cosine x squared, what? Times 2x. See? So that 2x was actually just part of the package and is not providing us anything extra to do. It's just, it's there because of the chain rule, and we were able to recognize it. Okay, what about if we had a problem like this one? How would you solve it?
Inverse tan 2x.
You're very close. You recognize that this looks sort of like an inverse tan? Well, you obviously recognize that.
Is it x squared?
Okay, if you look at this, it looks like kind of an arctan. It also looks like some other things, but one of the closest matches we have is an arctan. Maybe it's just an arctan problem in disguise. If it is an arctan problem in disguise, maybe we can rewrite it so it looks a little more like an arctan. Isn't the bottom supposed to be 1 plus something squared? Okay, so let's write it like this. 1 plus x squared squared. Okay, the answer to this problem is simply arctan of x squared, of course, plus c. Why? Because what is the derivative of arctan x squared?
Oh, 2x plus.
It's 1 over 1 plus x squared squared times 2x, right? Which shows up on top. See it? It works. And of course, plus c goes to 0 when you take the derivative. So am I just doing like a guessing sort of thing where I'm trying to undo the chain rule? Right now we are, but let me show you how you can do these problems more methodically. Okay? So what a person would typically do with a problem like this is, they would probably recognize that it does have something to do with arctan. Okay, so let's redo this problem, this time with a little bit more structure, instead of guessing and checking. This is called substitution. The person would look at this and say, I see a 2x in this problem. Maybe there's an x squared somewhere, because 2x is the derivative of x squared. Where's my x squared? Where is it? Well, it's buried in the x to the 4th. So they would rewrite the problem like this. And they would write this, let u equal x squared. Okay? So now the problem looks like this. Starting to look a little simpler. And after writing let u equal x squared, they would then take the derivative of this. Now I know this is an antiderivative problem, but they're going to take the derivative of this. So what is the derivative of x squared? 2x, right. So we could write that du dx is 2x. Isn't that true? Or you could write that in differential form as du equals 2x dx. Why write it like that? Because look, 2x dx showed up in the original problem. See that? So then they would replace the numerator with du. And then they would realize, oh my goodness, this really is just an arctan problem. It's arctan u.
How do you get du equal?
Plus c. In other words, arctan x squared plus c. Say again?
I don't understand how the du over 1, I get the 1 plus u squared, but what is du? Like, how would you know that's going to equal?
Okay, so let's try and do this again. We saw the 2x and we suspected that there might be an x squared buried somewhere in the integrand. We were able to hunt it down. There it was, buried in the x to the 4th. So we declared this x squared to be our u for the problem. This is called u substitution. Great name for it. By letting u equal x squared, and then du dx would be 2x, right? And therefore du 2x dx. We can rewrite this integral entirely without any x's. So we rewrote the top as just simply du, and the bottom is simply 1 plus u squared, and this problem became So we suspected it might be an arctan, but we were actually able to write it in exact arctan form. That's the answer. U, of course, is x squared. Find answers here. Let's take some practice. Let's try another one. Okay? It's really the chain rule in reverse, but it's methodical. So you don't have to guess the answer. You can actually have a process to follow. Okay? So let's go ahead and go to the next one that I picked, and it's this one. What is the integral of x square root of 1 plus x squared? This is a really hard problem. Like, this problem would be very, very, very challenging. Like trying to guess the antiderivative? Are you kidding me? Okay, but I'm going to show you exactly what to do. You'll notice that there's an x here. So I'm guessing somewhere there's an x squared in this problem. Isn't it true that there's an x squared in this problem? The reason I say that is because, yeah, if this is the derivative of something, right, he's probably just the result of the chain rule. So he's the derivative of somebody who is buried inside somewhere. So look at the inside here. 1 plus x squared. What's the derivative of 1 plus x squared? 2x. Not far off, is it? I have an x. The derivative of this is 2x. Okay, so here's what I'm going to do. I'm going to let u be 1 plus x squared. Okay? And let's find the derivative of that while we're at it. So what is du dx? 2x, right. And if I write that in differential form, it's du equals 2x dx. So what I really like about this problem is, so far I've gotten it to where I can now rewrite this part as simply u. That's beautiful. Look how much simpler it looks. And see this x dx right here? That x dx, that shows up in my work right here. See it? Okay, so what I'm going to do is I'm going to isolate x dx in my red work down below. X dx is evidently 1/2 du. So I'm going to substitute that in. This problem is a piece of cake now. I've rewritten the integral. In fact, I can even put the 1/2 out front if I want. And why don't we just call this u to the half? That makes it a little bit easier to understand. Okay, so what function would have derivative u to the half? That's right, 2/3 u to the 3/2. You want to explain that, Aaron? That was good. You've obviously practiced that before. So you added 1 power to the half. Good, that's 3/2.
And then I just took the reciprocal. I'm sure there's a better way to do that. I just took the reciprocal and put it down there because I knew it was going to multiply down.
Yeah, you add 1 power. That's exactly what I would have said. You add 1 to your power, and then you simply multiply by the reciprocal of that in the front. And if you look at this closely, it reduces a little bit. It looks like our answer is 1/3 u to the 3/2. Don't forget the plus c. And the derivative of this really is 1/2 u to the half. It really is 1/2 u to the half. And now we can put in what we meant by u. U originally meant 1 plus x squared. So let's put that back in. This is a very powerful method. This is the antiderivative of what we started with. If you take the derivative of this answer, it gives you that integral. Beautiful. Okay. Let's go to the next one. Let's find the integral of sine x e to the cos x. This looks really awful. Really, really awful. But where have we seen problems like this, where the derivative pops out as e to the something? Any problem that has e to the something in it, the derivative will be e to the something. Isn't that true? Okay, so it looks to me like this is sort of the core part of the problem, you know, and this is just sort of the chain rule, maybe. That sine x is there because of the chain rule or something, right? So what I'm going to do in this problem is I'm going to actually declare cosine x as my u. Okay, watch this. I'm going to let u equal cosine x, which allows me to write the problem like this. See? Because I'm not afraid of integrating e to the u. That's easy. After writing down that suggestion, we need to find the derivative. So what is the derivative of cosine? So du dx is negative sine x. Let's write it in differential form. So that usually just means move the dx over. And look, if you look closely, the original integral had a sine x dx in it. See it? And your work has sine x dx in it. That's good. Okay, the only thing is it's negative. What am I going to do with that? Let's move that negative to the other side. Negative du equals sine x dx. Okay, now I have a replacement not only for cos x, but for sine x dx. See? I get rid of the cosine x by calling it u. I get rid of the sine x dx by calling it negative du. So it's going to look like this now. And this is a little jumbled up. I'm going to put the du at the end, of course, and the negative in front. Okay, that problem doesn't scare me at all. That's a snap. What is the antiderivative of e to the u? Du. It's just e to the u, right? So the negative's out front there. The answer is e to the u. Don't forget the plus c. And of course, by u we mean cos x.
How do you know what to make u?
That's the question. That is the hardest part of this, is to guess as to what you want your u to be. I've tried u's before and it didn't work. And then I've changed my mind and tried something else, and it worked. So sometimes the answer to that question is a little trial and error. Okay? Let's try this one real quick.
Could you have made it e to the cosine x? U?
No. Okay, let's try that. So this is the problem we just tried, right? And I had said that I was going to let u equal cosine x, and everything worked out beautifully for me. But that's coming from experience. I've done this before, so I knew that that would be a good choice. Let's say that you had tried to use the sine x instead. Watch what happens. When you do your du, you get cos x dx. The problem is, there is no cos x dx in this problem. See? Look at the problem, the original problem. There's no cos x dx. So that was a bad choice of u. Sometimes that's the only way you know. Okay, let's say you said, all right, fine. I'll use the e to the cos x. Okay, fine. Well, what's the derivative of e to the cos x? It's e to the cos x sine x, right? But you've already replaced this with u. Where are you going to get another e to the x sine x dx? Or e to the cos x sine x dx? You don't have enough junk in this problem to make the substitutions. So now your u is too complex. Okay? Let's try this one. Let's say you have integral x squared square root 5, actually let's do cube root, 5 plus 2x cubed. So this is an x squared in the front. And then we have a cube root of blah, blah, blah. How do you know what you're going to make your u? Well, there's actually several ways you could do this problem. You could actually pick the 2x cubed as your u. You could pick the x cubed as your u. You could pick the 5 plus 2x cubed as your u. Actually, all three of those methods would work. The easiest thing to do is to pick all of this junk, the 5 plus 2x cubed, and call it u. Okay, so let's circle this and call it u. Hey, u. u shall henceforth be 5 plus 2x cubed. Okay? Now, u represents that whole inside, which is good because we like simple radicands. We don't want a messy radicand. Du is just the differential for that. So it's just 6x squared dx. Do you see a 6x squared dx in the original problem? I do not see a 6x squared dx. I see an x squared dx. See it? It's right here. So I don't want that 6 there. So I'm going to put 1/6 du equals x squared dx. There we go. And now I can rewrite this entire integral without any x's. The x squared dx is going to be a 1/6 du. The cube root of 5 plus 2x cubed is simply cube root of u. Beautiful. So simple now. And let's go and write that in power form. So u to the 1/3. So Aaron said it well when he said that we would add a power and then multiply by the reciprocal of that new power. So if you add a power to 1/3, what are you going to get? 4/3. And then let's slap a 3/4 in front. And don't forget the plus c. This is the answer, but as a courtesy, let's change u back to 5 plus 2x cubed. And let's clean it up a little bit. So we have 1/8 times 5 plus 2x cubed to the 4/3 plus c. So how do you pick your u? You want to pick a u that makes your resulting new integral look a little cleaner. At the same time, it needs to be relevant. So you don't want to pick like too much or too little. If you pick too little, let's say you just pick x cubed, this problem would work, but it get a little bit gnarly at the end. I picked a nice big u right there, and look how simple my integral was. Okay. This is very hard to teach, okay? And it's very hard to see if you understood that. So I'm not going to give you homework due tomorrow, but the assignment's due the following day. Okay, because I want to work on this for a couple nights. This is kind of complicated. So tomorrow we'll do some more examples. I'll record those too, but I'm done for today.